Now, kernel PCA is sometimes really hard to comprehend because it's really a little mathy and nasty. So consider this as a challenge. I wouldn't somehow expect you to do kernel PCA in the exam, but yeah, maybe you can get through the whole thing and yeah, use it, because it's really a mighty tool. So kernels, just recall, we had this yeah, kind of yeah, trade-off between curse of dimensionality and blessing of dimensionality. If we're talking about kernels, we are typically in the context of a blessing. Maybe you recall from KDDM, whether you heard it or not, last semester or some further semesters earlier. Maybe you recall this problem that something is not linearly separable, but you want to apply a linear model like a support vector machine and stuff like that. Yeah, so you want to distinguish between the classes by just applying a kind of linear model, like a linear hyperplane, dividing the data space into two spaces. In one space there's class 1, and in the other space there's class 2. So that only obviously only works if you can really plug in such a linear decision boundary. And if you can't do that, well, first of all, it seems that these linear models are helpless or useless, but you can apply the kernel trick, if you recall. So you blow up the feature space by some super relevant features, and that is the blessing of dimensionality in that case, yeah, because you take relevant attributes and add them so that you make the problem linear in easy words, yeah, in simple words. Okay, so let's have a look at kernel PCA, how you can use kernel PCA also to, yeah, somehow transform the data. I mean, PCA is a transformation of the data, of the original data, into a new space. Because of the specific property of PCA having these decreasing eigenvalues, yeah, we know that if we omit the last eigenvectors or eigenvalues, meaning that we don't consider the last eigenvectors, we don't lose too much, or we are optimal with respect to loss of variance. Yeah? And the same can be done now with PCA, but not with a linear combination of original features, but with an arbitrary combination of the original features. Yeah? So we can look for arbitrarily oriented directions of higher spread, and can do the transformation in the corresponding feature space first of all, and then of course also try to reduce the feature space by just omitting the components that have the lowest variance. Yeah? And that's how we do or what we do with kernel PCA. So let's have a look at kernel PCA. First of all, once again, the idea of this kernel trick, yeah, we have these two following scenarios here. Here we have a linear correlation among the features. Here we have a non-linear correlation of the features, so that seems to be a quadratic correlation or relationship between x and y. Yeah? So in this case here, obviously PCA as we know it is absolutely effective because we have this linear correlation, and PCA will find this as the first axis, as the first principal component, and everything is fine. Here, if we apply principal component analysis, we may find something like this here. Yeah? This may be the direction of highest spread, which is not actually what we want, yeah? Obviously. So we would like to have this blue line, blue curve in that case. Yeah? Yeah, we can only find these linear models, and that is obviously a quadratic model in that case, so that is not a non-linear model, so we cannot find non-linear models in that case. So and that is yeah, the solution comes from linear classifiers, for example support vector machines, as we just said, where we have to make non-linear problems linear, yeah, by using suitable feature mappings, especially by blowing up the feature space. So here is an example where we want to distinguish between the green observations and the red observations. Obviously we cannot find a line. This is a two-dimensional case, so a linear model would try to find a line that separates the two observations, or the two sets of observations, the reds from the greens. But obviously there is no line to draw in this data space, so that we have on the one side of the line the red ones, and on the other side the green ones. Yeah, so there is no linear separation possible for these two classes. So it's a non-linear problem. And the solution with support vector machines is, well, first of all, to introduce, of course, a soft margin, but that doesn't help here. So we need to make this non-linear problem linear, and we can do that in this case by just pumping up the two-dimensional space by a mapping to a three-dimensional space. Yeah, we just introduce a third dimension, which is a combination, a non-linear combination in that case, of the original ones. Yeah, so we have the original features are x1 and x2. Yeah, x1, x2, for example, and we just map this original feature space with two features, x1 and x2, to a three-dimensional feature space. We keep the original two features, x1 and x2, but the third feature is a combination of the original ones, which is a nonlinear combination in that case, because we take x1 squared plus x2 squared, which is actually the is related to these circles, of course, obviously. Yeah, and you see the mapping here. If we plot the mapping here in this three-dimensional space, then you see, well, it's close, but you can now separate the greens from the reds by a hyperplane, a two-dimensional plane, which is somewhere here. Yeah, you transfer a non-linear solvable problem into a linear solvable problem. That's the idea of support vector machines, and that's the idea of kernels, first of all. Yeah, because you don't want to make this mapping actually explicit, but you want to somehow describe that mapping by a so-called kernel function. So that is the next point, and that is the kernel trick. Yeah, we don't want to have a high-dimensional mapping explicitly done, because that still have some or can have some negative impacts, some aspects from the curse of dimensionality still. Yeah, so in that case, whenever it's possible, we try to use the so-called kernel trick. What happens to the M here? That should read KDDM lecture, of course. Yeah. So if you want to have a closer look in the KDDM lecture, I think Matthias Renz did some, at least some words on the kernel trick. But anyway, so what is the kernel trick actually? Well, if the intended mapping phi is something, the kernel is usually defined as the dot product of these mappings here of original feature of original observations x and y. So x and y are original features. Yeah. So once again, we have, for example, this situation here. So x and y are observations from the original features, from the original feature space, which is two-dimensional x1, x2 here. Yeah. So x and y are original features. We have to map them to a high-dimensional feature space. In that case, the mapping is from x1, x2 to z1, z2, z3. z1 is x1 squared. z2 is square root of 2 times x1, x2. And z3, the third feature, is x2 squared. Yeah, so this is x1 squared, this is x2 squared, and this is x1 times x2 times square root of 2. Yeah? And this mapping, which is here explicit, can hopefully be modeled by this mapping function phi here. Yeah? So the mapping here is this is the mapping function here. Yeah? So each original observation x, consisting of two features, is mapped to three new features, and the three new features can be computed from the original features as given here. Yeah? Then the so-called kernel is defined as the dot product of the mapped features. Yeah? So the kernel between two observations is the dot product of the two observations mapped to the higher dimensional feature space, or to the different feature space, to the new feature space here. Yeah? And this here is an explicit example for the so-called degree 2 polynomial where the degree is degree d polynomial, sorry, where the degree d here is 2, yeah, so it's degree 2, so quadratic correlations, so to say, or quadratic relationships, and the kernel function can actually be rewritten as, so this kernel function here can actually be rewritten as x transpose times y. Yeah, x and y are the original feature, original objects, original observations from the original feature space, plus c to the power of d. So you see that we don't need to explicitly transform the x into the new feature space and the y into the new feature space. We can just simply work on the with the original representations x and y. So x and y are the original representations from the original feature space, and we can compute the similarity between x and y in this new feature space phi of x and phi of y without explicitly applying this this transformation here. Yeah, so computing this formula here actually is the same as computing this one here by applying phi, the transformation, explicitly. Yeah? So that is the trick that prevents us from transforming each object, each observation in the data set into the new representation. Why is that good? Well, sometimes this phi here, so here is this mapping, this phi mapping here is not so complex probably, but still you have to do it if you want to do it explicitly. Yeah, but sometimes the mapping can be a little bit more complex, and sometimes even cannot be really computable in some sense. Yeah, so if you think about a Gaussian kernel or stuff like that. Yeah, so that is the kernel trick that you this kernel function here. So the dot product is actually a similarity measure, obviously, between x and y in the new feature space, which is obtained by mapping the original feature space by this mapping function phi here. Yeah? And the trick is that you don't have to compute this mapping phi explicitly, but you can work in order to compute this similarity in this new feature space. You can work with the original feature representation. That is the kernel trick.